Hello, and welcome to Astronomy 100. In this video, we're going to start a new section of astronomy that's called Stellar Properties. And in this section, what we're going to do is describe all of the measurable properties that involve things that we can learn about the stars. There are many properties that stars have, and of course, many of these properties are things that we want to know about the stars. In a previous segment, we've talked about at length about how we determine the chemical compositions of the stars, and we also talked about how you can determine the temperatures of the stars. Both of these things are something that can be determined by the light that the star is giving off. But there are many other things that we want to learn about the stars as well. For instance, we want to know how far away the stars are. We want to know how big the stars are. We would like to know how the stars form, how they live, how they die. We would like to know how much energy the stars are producing and how bright the stars appear to our eyes. And so there are many different properties that astronomers are interested in when they are learning about the stars themselves. Now, many of the same challenges that we've had in the past are still in play here, and that is that the stars are, of course, very far away from us, and the traditional means that we would use to measure things about the stars, we just don't simply have available. For instance, if you want to know how big a star is, we can't simply go to the star and use a measuring tape to figure out how big the star is. So there need to be workarounds or alternative ways that we can learn these properties of the stars, but by doing so remotely, being here on the Earth, looking at the stars in the sky. So what we're going to do is begin down that road of describing all these properties. And the first thing that I want to discuss today is the concept of the difference between luminosity versus brightness. So in this picture here that you see on the screen, this is a photograph taken of a city street, and you can see in the photograph that there are many street lights lining the street going up and down the block. Now, what I want you to think about for a moment is how each and every one of these street lights is identical to all the other ones. So the exact same make, the exact same model, the exact same light bulb is used in every one of them. But you'll notice that when you look at the brightness of the street lights that are close to you, and when you look at the brightness of a street light that's very far away, they appear to be very different in their brightness. But luminosity is not the same thing as brightness. Luminosity is the energy that the lamp is producing. Brightness is how we perceive that energy. So what we would say when it comes to this particular picture is every one of these lamps has the exact same luminosity, but the appearance of the brightness of each and every one of these lamps is different. So what I'm going to do is show you a couple of definitions to help reinforce and get this idea across. The first one is, if we were to define the concept of luminosity and define the concept of brightness, and in doing so, we're going to use an example of a light bulb here. And you'll notice that the light bulb is producing light. That light is going off in all directions. And you'll notice the word luminosity here on the bulb and the word brightness up here. And we'll come back to that in just a minute. Here is the definition of luminosity. Luminosity is the amount of energy that is radiated by a star, or in this case, the light bulb, each second. So it's the amount of energy that the star is physically giving off, putting into space that goes off in all directions. Now, the brightness of a star, or a light bulb in this case, is the amount of energy radiated by the star that is received by an observer at some particular distance. Now, what you want to think about is luminosity is the energy that the light bulb is making, that is leaving the light bulb. Brightness is how much of that energy is getting to you at the distance that you happen to be. So there is a fundamental difference between these two. For instance, luminosity is something that does not change unless you change the amount of energy that the light bulb is producing. But brightness is always changing with your changing distance. So to show you the idea, let's put some imaginary eyeballs here. Let's say that you are at this location, very close to the light bulb. What you'll notice is there is quite a bit of light that reaches you because you're very close. And so the light bulb will look very bright because you're very close. if you now move at this distance, you'll notice that the light that is now reaching you is more spread out, and so the amount of light that reaches you is much less than what it was over here. Even though the light bulb is producing the same amount of energy, the amount of light that gets to you is based on your distance. So the brightness of the light bulb is different for this person than it is for this person, even though the luminosity doesn't change. So luminosity is the amount of energy that is being produced, and the brightness is how much of that energy gets to you at the distance that you happen to be. An important idea is that you can't ever see luminosity. Luminosity is not something you see. You are always seeing brightness. And the reason why that is because you can imagine this light bulb is putting light out into space in all of these directions. But if you're right here, the only amount of light that actually gets to you is the light coming in this direction. There is no way that this person can see the light that's going off over here. So you can't ever see or take in all the light, you only get a small fraction of the light. So it's really very critical that you understand that there is a difference between luminosity and brightness, and that the luminosity is the energy that the star is actually making and producing, putting into space, and the brightness is the amount of that energy that gets to you. So what we're going to do is we're going to talk about each of these individually, and of course the first one that we're going to discuss is the concept of brightness. In astronomy, brightness is a term that's a kind of a loose term, and brightness, of course, is very subjective. What may seem bright to you may not seem bright to somebody else. So we can't necessarily use the word brightness to indicate what we are seeing. In astronomy, instead, we use a word that is magnitude. And the specific term that we use is called apparent magnitude. It comes from the word appears, and the apparent magnitude of a star is defined as how bright the star appears to an observer on the Earth. It could be any object. It could be how bright a galaxy appears, it could be how bright a planet appears, it could be how bright a star appears. But the important thing is it's how bright that the object appears to somebody on the Earth looking out into the sky, looking out into the universe. So let's use this picture as an example. Each of these stars is producing energy, so therefore each of these stars has a luminosity. But we are also seeing the appearance of the brightness of these stars. Now, some of these stars could be very far away, some of them could be very close, we just don't know. What we can say for certain is that this star appears very bright and one of these stars appears very faint. So the appearance of brightness is something that we can actually judge simply by looking at the star. We can't determine the amount of energy the star is producing unless we know its distance. So what we need to do is quantify the concept of brightness. You can't put the word bright or faint into an equation. So we need an actual number that will tell us the indication of the appearance of brightness. So apparent magnitude is the term, and you'll notice the abbreviation is lowercase m. So this is the symbol that we use for apparent magnitude. How do we attach an actual number to the concept of apparent magnitude? It's something that, of course, is very subjective. As I said, what you might judge as being a certain brightness, somebody else might judge to be a different brightness. So the very first attempt to try to attach a number to the concept of the appearance of brightness goes all the way back almost 2,200 years ago to the year 129 BCE, and it was a Greek philosopher by the name of Hipparchus. Now, what Hipparchus did was something quite simple. He would look at the sky, and he would look at all of the stars that you could see, and he would simply judge their brightness as different levels of brightness. And he created different categories of brightness based on the appearance of how bright or faint the star is. So let me show you how he does this. What he does is he judges the brightest stars in the sky and calls them first magnitude stars. So these are the stars that would appear the brightest to your eyes, and those are the first brightest, or first magnitude. Then the stars that were a little bit fainter, he called second magnitude. The stars that were collectively fainter still were third magnitude, and then fourth, and then fifth. And it turns out the faintest stars that he could see, just barely see, ended up being sixth magnitude. So he judged the levels of brightness first magnitude stars being the brightest, and 6 magnitude stars being the faintest, just the limit of what you can see with your eye. Now, what I want you to notice is there's something that's a little awkward about the way that he did this. Notice that the stars that are the brightest have the smallest number, and the stars that are the faintest have the largest number. So in science, we call this counterintuitive, meaning it's not quite the way that you would expect to do something. It's just, it feels backwards. The bigger number is actually the fainter star. And the way that he did this, there's nothing wrong with it, but it just seems a little bit odd. Now, I wish I could tell you that we have since changed this in the 2,200 years since he came up with this system, but the reality is we have not. So modern astronomy still uses this very backwards nature, and so you'll need to get used to the idea that bigger numbers mean fainter looking objects, and it takes some practice to get used to that. Now, there were some additional problems with his system. For instance, Hipparchus did not include the moon, he did not include planets, he did not include the sun in all of these numbers. He only included the stars. Well, today we know, of course, the sun is a star, and we have to also include other objects that you could see by giving them numbers as well. So we had to make some modifications to the system to be able to do this. And let me show you what those modifications are. The first thing that we did was to include the brightest objects in the sky, something like the sun, which is far brighter than any star. We had to go into negative numbers. So there is such a thing as a negative magnitude. An example is the sun's magnitude, the appearance of the brightness of the sun, is more than -26. So it is very deep into the negative numbers because it is a very, very bright object. As you go less than 1, you go into negative numbers. Now, this also means we had to include 0. So 0 is an actual brightness, which feels kind of odd. The brightness of an object can be 0, which just seems weird. But there is such a thing as a brightness of 0. The other thing we had to do was, after the invention of the telescope 400 years ago, we now know that there are stars fainter than what you can see with the human eye. To include the fainter objects that you would see with a telescope, the numbers are now made so that they go bigger than 6. So if you have an object that is 7th magnitude or 8th magnitude or 9th magnitude, it is actually fainter than what the human eye can see and would require a telescope. So the numbers go bigger than 6. The additional thing that was done is, because we have very accurate ways of determining brightness with electronic instruments now, we don't have to stick with integer values. So we now have decimals. An example is you can have a magnitude that's 4.32 or a magnitude that's 1.82 or 2.99. So we have decimal values as well. Now, the last part of this is an important part, and it has to do with the appearance of brightness. What I have on the screen are an example of stars of different brightness. So we have 1, 2, 3, 4, 5, 6, 7 stars, and each of these is an example of stars of different magnitudes. First magnitude, second, third, fourth, all the way through 7th. Notice the brightness is decreasing while the number is increasing. So a 6th magnitude would be the faintest you can see. A 1st magnitude would be the brightest of all stars. So astronomers were curious. What is it that is the difference in brightness that when you go from the 1st magnitude to 6, which was Hipparchus's original set of numbers? The brightest stars in the sky were 1st, the faintest were 6. Now there's a difference of 5 magnitudes there. So the question is, what is the actual difference in brightness when you jump 5 magnitudes? The difference between the brightest and the faintest. The other question that was asked is, what is the difference between one single magnitude? So in other words, how much fainter is a 2nd magnitude compared to a 1st? So the way that they did this is they went outside with electronic instruments and they measured the brightness of a 1st magnitude star, and then they measured the brightness of a 6th magnitude star, and they compared the numbers. And what they discovered is any 5 magnitude differences was a difference in brightness of 100 times. So a 1st magnitude star is actually 100 times brighter than a 6th magnitude star. Now it's any 5 magnitudes, so the difference between a 2 and a 7, which is 5 magnitudes, is also a difference of 100. So any 5 magnitude step difference is a difference of 100 times. Now when you want to figure out what is an individual magnitude, just a little bit of math. All you do is take the fifth root of 100, because some number multiplied by itself 5 times equals a difference of 100, and you end up getting 2.512. So what that means is any one single magnitude step is a difference of 2.5. A second magnitude star is 2.5 times fainter than a first magnitude star. Now, this numbering system is a little bit challenging to get used to, and I encourage you to try to make sure that you understand how this works. In the next video, we'll see an application of how this system works. I hope you'll join me.